Section 2.1, vectors in the plane. So to start with, we want to define what is a vector. So a vector is a quantity consisting of two separate things, a direction and a magnitude. Magnitude is a fancy word for length. I will oftentimes switch between these two words, but they mean the same thing. Okay, a vector can be depicted like this. So you can see this is the vector v. It's a directed line segment. It's an arrow. Okay. One thing, in print, vectors are typically denoted with a boldface. I mean, some texts might even denote them just with usual math font. But when you are writing these things by hand, it's not really possible to write things in bold. So the other way is to write things with write a vector with an arrow over top of it. So something which looks like that, for example, which I've also typed out like that. But yeah, so that is notation for vectors. The book uses this terminology. So the book calls the two ends of the vector particular names. So it calls this guy, this point, it calls it the initial point, and it calls this other point the terminal point of the vector. Okay, so just so that we can actually reference things at times, we sometimes use this terminology. And so a vector starts at the it's a line, it's an arrow that is constructed by starting at the initial point and going to the terminal point. The length of this vector, or the length of this line segment, represents the magnitude of the vector. Okay. And a notation for magnitude. So if we just are given a vector v in bold and we want to get its magnitude, we can use this notation of surrounding it with these double vertical bars. Right? That's the way that we denote magnitude of a vector, or take the magnitude of a vector. Some references might use this notation instead, using these absolute values, because you usually think of absolute value as being as meaning length, right? On the number line, it is the distance from of the number to 0. So in a way, this notation makes sense, but that kind of conflates things a little bit too much, in my opinion. So I will prefer to use these double bars to denote magnitude of a vector instead of kind of mixing that idea with the idea of absolute value. Okay. Right. So 0 vector. This is kind of a thing that can arise. It's a bit of a funny concept. So we're defining a vector in terms of an initial point and a terminal point, and the vector itself is the thing that connects you from the initial point to the terminal point. So one question that you might ask is, well, what if the 2 points are the same? Well, if that's the case, you get this funny thing called the 0 vector, right? Its length is 0 because it doesn't go anywhere, and you might denote it with a 0 in bold, or perhaps a 0 with an arrow over top of it. This 0 vector is a bit special. It's like the only vector that doesn't really have a direction to it, and so it can be considered to have any direction that is useful for the problem that you have. Okay. Okay. Now that we have these objects called vectors, one thing to ask is, well, how do we describe when two vectors are equal? How do we describe when they are the same? And so this terminology that we have is equivalent vectors. So we say that two vectors are equivalent or equal if they have the same magnitude and direction. And here's a little picture illustrating this. So with the vector v and the vector w, you can see that they both have the same direction, for sure, you can see that. You can also kind of check that they have the same magnitude, but just kind of putting your hands on the screen and sliding them over from v to w, you can see that the magnitudes are the same. The lengths of these line segments are the same. So these vectors are equivalent. So because we are treating this idea of vectors being the same, having the same direction and magnitude, we use this as our notion of equality. So we denote them being equivalent by using the equal sign. So v is equal to w in this picture. Okay. Another thing that can happen is that we might be describing things in terms of points, right? The initial point and the terminal point. And constructing a vector out of these 2 points, we would use this notation PQ with an arrow over top, okay? The way you read this is the vector going from P and ending at Q. So if I were to maybe draw this pictorially, say you've got the point P over here and the point Q over there. The vector PQ starts at P, goes to Q. Okay, so this would be the vector PQ. And as I am alerting you in the notes, the ordering of the letters is important. So if you were to reverse it, QP, this would actually start at Q and go to P. You would end up with a vector in the opposite direction. Okay, so yeah, the order matters, and you have to pay attention to it. Okay. Now that we have these things we call vectors, we want to start doing stuff with them. What we can do, there are certain operations that we're going to introduce now, and then there can be more operations that we'll introduce later. But for now, we are going to deal with 3 things: scalar multiplication, vector addition, and vector subtraction. So starting with scalar multiplication, well, first of all, the word scalar it just means a real number. It's and the term itself is kind of used to sort of suggest that you scale something. So we're kind of scaling the length of our vector up and down. That's what scalar multiplication does. When we multiply a number by a vector, which this is kind of the way that you would see this denoted, k times v. K is some real number, and v is the vector in question. You scale that vector up or down, depending on what v is. And if k is a negative number, then the direction ends up being reversed. And there's a little comment that if k is -1 specifically, then usually you write this with a minus v instead of -1 times v. So the negative of a vector just means that we're multiplying the vector by -1, which just means that we're reversing the direction of the vector. That comes into play with subtracting vectors, as we'll see shortly. Let's also just think about what this graphic, this figure is showing. So if we start with a vector v depicted as part A, then in part B, you see that 2 times v, it scales up the vector v. So these 2 vectors have the same direction, but their magnitudes are different, their lengths are different. 2v has twice the length of v. If instead you multiply by something that's less than 1, like a half, then you end up shrinking the length of the vector, as C shows. And then in D, we multiply v by -1, which reverses the direction of v. You can see that the lengths are the same, but instead of going in the up right direction, we go in the down left direction. We've reversed the direction of our vector. Okay. Moving on to vector addition. So adding 2 vectors, the notation is what you would think it is. There's 2 different ways to visualize this, which the book goes into. Note that what we're doing right now is doing these operations in a coordinate-free way. Right? We don't have a coordinate system in our space at all yet. We will introduce a coordinate system momentarily, but for right now, we're sort of illustrating that these operations are actually geometrical constructions. They don't need a coordinate system to take place. They can take place in just whatever space we're working in. Okay, so, all right, how does this work? So the left one depicts the triangle method, and the right one is the parallelogram method. I think the triangle method is the easier one to think about, but I'll discuss both of them. So what's going on is that you suppose that you have 2 different vectors. They shouldn't, let me move W to be just somewhere else in space. It can be anywhere. So this vector w should look similar to that vector w, same length and same direction. When you add, so the procedure for adding two vectors under the triangle method is that you line them up tip to tail. Okay, so you can see that or head to tail. So the head of vector v, the tip of it, if you slide the tail of w to meet the head of v, then you end up getting this composite path, right? Traveling through v and then traveling through w. The net result would then be the addition, the sum of the two vectors. So v plus w is the overall path that is traveled, the overall distance, length, direction, I don't know, whatever you call it, but it's the overall thing that the overall travel. So you add these two vectors, you get that vector. And so that's the triangle method. If you use this parallelogram method instead, same w. Okay, so w is somewhere arbitrarily in space. V is this guy given. What you do is instead of matching them up tip to tail, you can match them up tail to tail, so that both their tails meet here. And then you draw out a parallelogram that uses these two as parts of its sides. So that involves you like sliding this v over here, this w over there. Those are the dashed lines. And then the sum is the diagonal of that parallelogram, stopping at the starting at the tails, and then ending at the tips. So initial point, terminal point, right? So either way, either procedure you use, you're going to construct the same vector. Okay. Right. So in looking at these triangles, there's something that the text sort of jumps into. It feels like a bit of a digression. It's not completely connected, but this does show up in the homework, and it is, we do need some idea about this in the homework. So let me just sort of follow this digression, which is that to do with creating an inequality out of the sides of a triangle. So let me sort of recall geometry with you guys. So say that you're just given a triangle, okay? So one thing that you should remember from geometry, and let me denote the sides of length A, B, and C. So one thing you should kind of know from geometry is that the side lengths satisfy the property that the sum of any two sides must be specifically greater than the length of the third side. So what you could write, the way you could write this is that a plus b must be greater than c, a plus c must be greater than b, and b plus c must be greater than a, right? There are three inequalities that you can generate from a triangle, right? Every triangle satisfies this. So the way you can kind of reason about it is that in order to create a triangle, the sides A and B need to not line up with C. So they have to take they have to travel a distance that is longer than the distance of the last side. Otherwise, so if they were equal instead, you'd end up getting just the triangle would degenerate and flatten out and kind of just turn into a line segment. You can imagine moving this point down, and that will make A and B and the sum A plus B then equaling C, which so triangles satisfy this. Now the triangle inequality is to do with vectors. So with vectors, we actually do allow the equality case, and in that case, what happens is that the vectors just line up with each other. They end up perfectly forming a straight line. So you could have like the vector v, and then plus the vector w, and they would line up perfectly to produce the overall vector v plus w, right? So that is what happens with equality, but otherwise you would get a triangle as in part A there in the figure. And then just to like read things off, you can see that this inequality is generated by just looking at it. So we take the sum of the side v, side w, add the magnitudes, the lengths of the two vectors, and that has to be greater than the third side of the triangle, which is the vector v plus w. So then we take the magnitude of that vector, getting the length of that side. So that's how these ideas connect. And in the homework, we will do that, but with a different triangle. We will end up actually working with this, well, a triangle related to this one. Okay. Right, so let's move on to now vector subtraction. Right. So, okay, we have just discussed scalar multiplication and vector addition. So it turns out that vector subtraction is actually just the combination of the two things. But I mean, just to kind of follow the buildup of arithmetic, we think of it as an operation on its own, right? The difference of two vectors. So the way that we define the difference of two vectors is we add the negative of the vector. And what do we mean by the negative of the vector? We mean we multiply the vector by -1. That's how we get the negative. So that's where this equality comes from, right? This v minus w is defined to be v plus negative w. And what is negative w? Well, it's -1, the scalar, -1 times w. We reverse the direction of w, and then add that vector with the vector v. That's how we do vector subtraction in this geometrical sense. Okay, and you can see graphically what this does. So if we start with v and w, as depicted here, what we have to do is, the way that I kind of think about this figure 2.6 here is actually to compare parts A and B with each other. So because what you need to do is you need to negate w and then add it. So it kind of combines these two things in A and B. So you can see that w would actually be this dashed arrow here, and then negative w would be this guy up here. And then you've already translated it so that the things match up tip to tail. So it's doing the triangle method, and then the resulting, the net travel is this vector, which is the addition of v and negative w, which if you translate that over, you can see that's the same as this. So this is how we define v minus w, right? V plus negative w. Okay. Right, so now we've done all this stuff in this more coordinate-free way. Now let's impose a coordinate system. So now we give our space a coordinate system. It's going to be the Cartesian coordinate system. We want to be able to write these vectors in terms of the coordinate system. So the way that we sort of give a name to these vectors under this coordinate system is, so first of all, the way that we think about vectors is there are these objects that are floating in space, right? They're defined to be these objects with a length and a direction. So notice that we don't care about the initial point or terminal point, right? Just the length and the distance. So that basically means that we can slide the vector around, and we end up getting, well, these vectors that are equivalent to the vector we started with. So wouldn't it be nice if we just had the initial point be at the origin, at 0, 0? That is the idea that we do. So for any vector that you're given, you can slide it so that the initial point is at the origin, which is kind of depicted in this picture. So starting with like this vector v, the initial point is at -3, 4 in this picture. What you can do is you can slide it so that it's at the origin, and then you can read off the coordinate of the terminal point, and that is the name that you would give to that vector. So the coordinate of the terminal point of this vector v is, the way you would write that is, let me bring this over. So you would write this as 4, -2 if we're talking about the terminal point, right? The point, 4, -2 in parentheses, that is how you would name the vector v. But instead of using round brackets, these parentheses, we end up switching over to these angle brackets for this component form of the vector. Okay. So this is how we associate to any coordinate in space. We can associate a vector that starts at the origin and goes to that point. That is how we can relate these two things. Okay. And yes, the bracketing is important. Right, and now here's another thing. So now that we're sort of imposing a coordinate system, it's good to get away from doing things geometrically now. We can kind of avoid the geometry. So, what happens is, so say that you have a vector with initial point at this coordinate xi, yi, and terminal point at xt, yt. Then what you can do in order to give this vector a name is you can use this expression. So maybe a bit of a diagram would help with explaining how this expression shows up. So let's say that that is xi, yi, and this is going to be a bit hard to do. So, and then this is xt, yt. Okay, right. So one thing to notice is with this angle bracket notation, the value in the x component, the value and the value in the y component, these are actually measuring how far you travel in the x and y directions. So you can see that this vector travels the distance. Maybe I'll use a different color. What color to use? It goes this way in the x direction, and then it goes this way in the y direction. And that, I'll just note the distance traveled in the y direction. So it ends up being yt minus yi. Right? That's the amount of travel in the y direction, and in the x direction, it's just xt minus xi. That's where this expression comes from, or that's another way of thinking about this expression. Instead of thinking about it geometrically in terms of translating the vector to the origin and measuring things off, we can think about it as breaking apart the components of the travel of the vector. Okay. And this is kind of, this example part here is just relating to this. So we could have done this process differently. If you note, so let's just read off the values. So the initial point here is -3, 4, and the initial is 1, 2. So -3, 4, 1, 2. Right, and if you want to compute what the vector, the way to write the vector in component form, you would just basically you take the difference of these two things component-wise. So you subtract the x's, subtract the y's, but you have to do them in the right order. Right? So it's terminal minus initial, 1 minus -3, and 2 minus 4, which gives you this, and then you compute it out, and you get 4, -2, which matches up with the geometrical way of doing it by lining it up and reading off the point. Okay. Okay, right, now we're converting over more notions. So, magnitude. So suppose that your vector is x, y. The formula to compute the magnitude, given this, is its distance formula, effectively. It's the square root of x squared plus y squared. So if this were your vector, then, well, the amount of travel in the x direction and the amount of travel in the y direction forms a triangle, a right triangle, from which you can use the Pythagorean theorem to determine the hypotenuse, which would be the length of the vector itself. So that's where this expression comes from. It should be quite intuitive. And we'll see that there's a generalized version for the third dimension once we talk about the third dimension. Okay. Right, and now the other operations. So scalar multiplication. If your vector v is x1, y1, and vector w is x2, y2, scalar multiplication, what you can do is just multiply the components of the vector, So you can see that the scalar gets multiplied into the components of the vector. And vector addition is just done component-wise. So you end up adding the x components, you add the y components, and that's the resulting vector. So it's quite easy to do compared to geometrically. And subtraction, you can imagine, is the combination of these two things, or it's just you end up subtracting the component-wise. Okay. Right, now this theorem in the book, I thought to include it, although it doesn't necessarily show up in exercises that you have, but it's just a way to think about the fact that what we're doing is we're really seeing that vectors, you can do arithmetic on vectors. They actually satisfy all these axioms that you probably saw, like the real numbers satisfy, like things like commutativity of addition, associativity of addition, additive identity, additive inverse. Like the numbers have these properties, and so do vectors as well. That's kind of nice. And yeah, other things. Distributivity is kind of a nice thing to look at as well. Whether or not this comes into play with computations, that might happen, but it's a nice thing to look at. Okay. Moving on. So unit vectors and normalization. So unit vectors are an important concept. They're the probably the nicer of vectors to work with. So unit vectors are vectors with a magnitude of 1. They have length 1. They're very useful things. Okay. So normalization is another thing. It's a procedure to convert a vector into a unit vector. So what you do is you rescale it so that it has length 1. So it is the unit vector that is in the same direction but of unit length. So all you have to do, and this formula kind of shows you what is going on, is you take given a vector v, you determine its magnitude, and then you divide by it. And what that will produce is it'll produce a vector in the same direction as v, but with length 1, which the book calls u. I do typically use u to denote unit vectors, but there is another notation that can arise, which is that people might use a hat. So you quite frequently, I think, you'll see that hats can emphasize the fact that your vector is a unit vector, or it can instead be used to denote the idea of normalizing the vector itself. Okay. All right. And the most important of the unit vectors are actually those that line up with our coordinate system. And these are called the standard unit vectors. Okay. So the standard unit vectors they use the letters I and J. And when you get to the third dimension, it uses K. So, but I and J just in 2D, you have 1, 0. So this one is in the X direction, and J is in the Y direction, 0, 1. So perhaps if we draw a picture of this, let's see. So let's say that this is where 1 and 1 are. Then these vectors are, I guess I made one of them a little bit, I didn't scale it correctly, but this would be I hat in the X direction, and this would be J hat, right, in the Y direction. Right? This would be in the X direction and Y direction of our coordinate system. And so now that we have these vectors, one thing that you can do is you can actually rewrite all vectors. These basically give you a different notation for vectors. Instead of using this bracket notation, you can write the vectors using I and J, because any vector in space can be constructed in terms of how far it goes in the X direction and how far it goes in the Y direction. And this will show up throughout the exercises. I don't prefer this notation, but there might be a reason for it. Maybe with physics it can be important, or with the cross product, but I will typically stick to the bracketed notation. Okay, right. So now on to similar problems. So I chose problems from the text that are similar to the homework problems. Uh, this blob of text relates to the first three, 1, 7, and 9. So uh, we're given these 3 points, and we are supposed to determine the vectors that are being asked and express them in component form and in a form using the standard unit vectors. Okay, so starting with this vector PQ. Right, so you have to remember that what we do is we start at P and go to Q. That means that we do Q minus P, effectively. So Q minus P in our computation. So you can see in the computation, you do 1 minus -1 and 5 minus 3, which is right there. And you compute that, you get 2 comma 2. And to write that in the other form with standard unit vectors, it's 2i plus 2j. 2 in the x direction, 2 in the y direction. Okay. For number 7. So notice that we can reuse some of our previous computation. We still have the vector PQ, although we need to scale it up by 2. We also need to do 2 times PR and then take the difference. So I start by computing the vector PR. So we're doing R minus P. Minus 3 minus 1, minus -1, and 7 minus 3, which gives us minus 2 comma 4. Then we end up needing to do this. So I'll just insert these values in. So 2 times the vector 2 comma 2, that's the vector PQ. And then instead of minusing 2 PR, I just add -2, right? That should be pretty easy to understand. And then PR is minus 2 comma 4. Okay, so then the next line, what I do is I'm using the way that scalar multiplication works, right? We have scalars outside of these vectors. We can push them into the vector by multiplying each of the components. So 2, we get multiplies the vector 2, 2 and becomes 4, 4. And minus 2 multiplies and you end up with 4 comma -8 here. And then lastly, we can add these 2 vectors. So we add component-wise. So 4 plus 4 gives you 8. 4 minus 4 plus -8 gives you -4. And so you get the vector 8 comma -4. And if you write this in the form with standard unit vectors, that's 8i minus 4j. Okay. Number 9. Find the unit vector that is in the direction of PQ. Okay. So this is the process of normalization. What you do is you compute the magnitude, the length of the vector PQ, and the vector PQ is given to us, and then we end up dividing. Right? So the magnitude requires us to use distance formula. So this is the vector we're thinking about, 2 comma 2. We take the magnitude of it, so you do 2 squared plus 2 squared, and you take the square root of that. So you get square root of 8, which is equal to 2 root 2. And so this is the magnitude of this vector. And what you want to do then is divide by the magnitude in order to create the unit vector. So that ends up being this quantity, and we can push the scalar in just to get us into probably the better form for writing the answer. So multiplying 2n, you can see you end up with this. You could rationalize the denominator, but I wouldn't bother with that. I would just write it like this. And then writing it in terms of standard unit vectors, you get this. Okay. Number 15. So this problem has 4 parts to it. You're given vectors a and b. In this particular problem, a is 2i plus j, b is I plus 3j. The point of this problem is to get you comfortable with doing these operations with the standard unit vector form instead of the component form, instead of the angle bracket form. So The way you do addition is you combine like terms, basically. So the i's combine together and the j's combine together. You just add them. So 2i plus I gives you 3i, and then j plus 3j gives you 4j. That's how you get the a plus b. And then writing this in component form, you get 3 comma 4. To subtract the vectors, that's what part B is asking. Take the vector difference, a minus b. You just subtract them, i's and j's, right? So 2i minus I and j minus 3j. And that's going to give you I minus 2j. And then writing it in component form is 1 minus 2. 1 comma minus 2. Okay. Now part C. So this is the thing about the triangle inequality. So first of all, we should just do a sketch to recognize that these three vectors form a triangle. Okay. So I think in the text it looked pretty much like this. So you have A, something's wrong. A, B, and A minus B. B and A minus B. So if I make the arrowheads work like this, so B goes this way, and then A minus B goes this way. So you can see that the net travel is the vector A, or you can see that, like, if you just think about addition in the kind of ordinary sense, if you take A minus B and then add B to it, you get A. So these three quantities do form a triangle, which means that the triangle inequality should be satisfied for these three things. Now, the text only mentions one triangle inequality, but I think that to do this problem correctly, you should actually consider all three of the inequalities. And basically, these three sides need to satisfy the three different arrangements, right? Meaning, like, yeah, if you take any two of the lengths, add them together, it should be greater than the third length. So in order to do this, we need to compute the three lengths. A is, let me scroll up a little, A is here. So we do distance formula to that. You square the x component, square the y component, add them together. Let's take the square root, so you get root 5. For B, B is this vector, so it's 1 plus 3 squared, so you get square root of 1 plus 3 squared, which is not 10. And then the difference, well, we computed the difference in the previous part, so we can just do distance formula to that. It ends up being 1 squared plus negative 2 squared, so you get 1 plus 4, take the square root, you get 5. So these are the three lengths of the sides of this triangle. And to verify that they satisfy the triangle inequality, we just make sure that if we add any two of them, it's greater than the third. And you can see that one of these checks actually ends up being duplicated. I can add root 5 to 10 in two different ways. I can pick different ones of them. But the inequality that we end up constructing is this one, which is obviously true. If we add, and then the last part of the triangle inequality would be the root 5 plus root 5 should be greater than root 10, which is this that I've expressed here. Now, maybe that's not as easy to see, but I would hope that you can do this mentally. What this really involves is noticing that root 10 we can express as root 2 times root 5, right? 10 is just 2 times 5. You can then break that radical over both of these factors. And then, well, you certainly have that root 2 is less than or equal to 2. It's actually less because root 2 is 1.4 approximately versus 2. So that's how we can do that mentally. We don't need to reach for a calculator to do that. Okay. Part D. So determine the vectors 2a minus b and 2a minus b. I think the only thing that this adds on is the scalar multiplication of the vectors, because we've already done addition and subtraction. And then once you have 2a and minus b, you can just add the two things to get this 2a minus b vector. Let me scroll out just a little bit to see. Okay, so a is 2i plus j, and so when you multiply this by 2, you scale up each of the components. You scale up the I component and the j component. So you get 4i plus 2j as a result. And then you can express it in terms of component form also, as 4 comma 2. For minus j, you just, well, you negate, or minus b, sorry. For minus b, you negate b. b is I plus 3j. Multiply that through by -1, and you get minus I minus 3j, which is written there. And writing this in component form, you get -1 comma -3. And finally, adding these two will give us the third quantity that's being asked. And we just add this component-wise, as we had done before. So combine like terms. So the i's combined together, the j's combined together. You just add them. So 4 minus 1 is 3, and 2 minus 3 is -1. And then writing this in component form, you get 3 comma -1. Okay. And this is the last problem. So it asks us to find the vector v with the given magnitude and in the same direction as the vector u. Okay, so we want to determine this vector v whose direction is the same as u, but who has the magnitude specified. Okay, so the procedure to do this is actually to, you take u and you normalize it, and then you scale it up so that it has the required magnitude, which is what I've written here. And that can be combined into one expression. So maybe I'll talk about this a little bit more. So normalizing this vector looks like this. We divide by its magnitude. So we end up with this expression. And then, so this is the unit vector in the direction of u, and then we scale it up by v in order to get the rest of the problem to match up. So multiplying by the length of v will scale this unit vector up to be of the length that we are asked. And then if you want, you can re-express this in this format, as I've done. So this is the overall idea of how we approach this problem. Now let's actually do it for these specific numbers. So computing the magnitude of u, you can see we again use distance formula. So it's square root of 3 squared plus -5 squared. So that's 9 plus 25, which ends up being 34. And take the square root of it. And so this is the length of u. We divide by it to give us, well, in the denominator, but then we also have to multiply by the length of v, which is 7. So we end up with this scalar in front of our vector u. And for completeness sake, we multiply this into the vector in order to get this expression. Right. And so that's the end of this section. Right. Vectors in two-dimensional space. And in the next lecture, we'll talk about vectors in three-dimensional space.